All right, this is the second half of chapter 20, and it's hypothesis testing, more about hypothesis testing. All right, so let's pick up on some important points. Okay, so confidence intervals and hypothesis tests are built from the same calculations. Okay, so that's an important concept here. Now, when we do a hypothesis test and a confidence interval, okay, the key concept also is that they have the same assumptions and conditions that we need to check. Now, what's cool about that is we can actually approximate a hypothesis test, okay, by examining a confidence interval. So just ask whether the null hypothesis value is consistent with the confidence interval for the parameter at the corresponding confidence level. So for example, in a hypothesis test, you would have the null hypothesis is that P equals some hypothesized value. When we construct a confidence interval, we have P hat plus or minus the margin of error, and we get an interval of two values, okay? So basically, we're looking to see if this value from a hypothesis is inside our confidence interval, okay? So we have two cases. Case one, if our hypothesized value, P0, is in our confidence interval, I'll call that CI for short, okay, then we fail to reject the null hypothesis. And in case two, if the hypothesized value, P sub 0, is not in our confidence interval, then we reject our HO. Now, because confidence intervals are always two-sided, they directly correspond to two-sided tests. There's no conversion factor. Okay, so in general, a confidence level of C percentage corresponds to an alpha level of 100 minus C%. So for example, okay, if you have a 90% confidence interval, that is going to directly correspond to a hypothesis test with an alpha equal to 100 minus 90%. Okay, and that's going to equal a 10%, which we know we translates to 0.01 for our alpha level. Now, whereas if you have a confidence interval and a one-sided hypothesis test, we have to remember to divide by 2. Okay, so for example, if I have a 90% confidence level and I look at a one-sided hypothesis test, okay, the corresponding alpha level would equal 100 minus 90% divided by 2, which equals 5%, which corresponds to 0.05 level for the hypothesis test. All right, so that brings us to example 8. So soon after the euro was introduced as currency in Europe, it was widely reported that someone had spun the euro coin 250 times and gotten hedge 140 times. So we wish to test the hypothesis about the fairness of spinning the coin. So in part A, we're going to estimate the true proportion of heads using a 95% confidence interval. And we're not going to forget to check the conditions. And then we're going to answer the question, does our confidence interval provide evidence that our coin is unfair when spun? And then we're going to explain. And then finally, we're going to see what the significance level of this test was. All right, I'm going to go to a new page here. So let's go ahead and do part A. All right. So this is example 8, part A. Okay, so here's A. All right, so we have to check our conditions whenever we calculate a confidence interval. So our first one, independence assumption. So the euro spins are independent. One spin is not going to affect the others. So with true independence, I'm going to change my zoom to zoom fit. This way I can see where I'm going here. Here we go. All right, that's better. All right. All right, now, so with true independence, it doesn't make sense to try to check the randomization condition or the 10% condition. But remember, these verify our assumption of independence. And we don't need that in this case. Okay. We do have to check the success failure condition. So n times p hat equals 140, and n times q hat equals 110 are both greater than 10. So the sample is large enough. Since the conditions are met, we can use a one proportion z interval to estimate the proportion of heads in euro spins. Okay, now for those of you who need a refresher here, okay, I'll show you the calculations here of how I got this interval. We are going to get 0.498 to 0.622. 0.622. Okay. Now you can go to the calculator. Okay. And I'll just do a quick refresher here. So you could go to calculator and you could go to stat. You could go to tests. And then you could go to option A, one proportion z interval. And you get the same answer. Or if you were doing this by hand, you would need the following pieces of information. You would need to know that our p hat was 140 divided by 250. So then the formula is p hat plus or minus z star times the square root of p hat q hat over n. So you have 140 divided by 250 plus or minus. All right, and we're going to construct 95% confidence intervals, 1.96 times the square root of 140 over 250 times 110 over 250 over 250. And then when you do this, you're going to get the exact same interval or close to it, depending upon where you round. And that's where that comes from. Now remember, it's not enough to report your confidence interval. You have to explain what that says. So we would say the following. We are 95% confident that the true proportion of heads when a euro is spun is between 0.498 and 0.622. All right, that brings us to part B. Okay, so since 0.50 is within the interval, there is no evidence that the coin is unfair. 50% is a plausible value for the true proportion of heads. That having been said, okay, and that's enough. And C, the significance level is 0.05. It's a two-tail test based on a 95% confidence interval. That was example 8. Okay. So something neat, and this is actually not a topic on the AP exam, that's why there's a star here, is you have a 95% confidence interval for small samples. So sometimes, okay, when either NP or NQ are not greater than or equal to 10, you can do a quick little trick here. You can come up with 4 additional observations and fix your sample size condition. Now, this really only works when NP is equal to like 8 or 9, or NQ is equal to 8 or 9. Okay? And what you end up doing is you add a total of 4 phony observations. You add 2 successes and 2 failures. So you get a new proportion. So remember, our p-hat, our population proportion, our sample proportion, is equal to the number of successes over n. So all we do is we fix this, and we call this p tilde, or the adjusted proportion. Sometimes you'll see this called p adjusted. Okay. And I just use p tilde. So you just take the number of observations, positive observations plus 2 over the sample size plus 4. Okay. And what that does is it gets to this success failure condition so that it's met, and it allows you to calculate a confidence interval. So here's the new confidence interval you calculate. Notice it's the exact same formula you've been dealing with. Okay, so in reality, by the way, isn't this really Q tilde if you want it to be consistent to what we've been doing? Okay. So the adjusted form gives better performance overall and works much better for proportions of 0 or 1. It has the additional advantage that we no longer need to check the success failure condition because we artificially change our sample size to make sure this works. Okay. So let's try example 9. So a survey of 81 randomly selected people standing in line to enter a football game found that 73 of them were home team fans. So A, explain why we cannot use this information to construct a confidence interval for the proportion of all people at the game who were fans of the home team. And then B, construct a +4 confidence interval and interpret it in context. All right. So I have this right here for us. This is example 9. And again, I'm just going to be a little bit more verbose than I was in class. So we cannot construct a confidence interval for the percentage of home team fans entering the stadium, since only 8 people were not home fans. The success failure condition is not satisfied. Okay, and I basically found that by taking 81 and subtracting 73, and that is how I got 8. All right, B. Okay, so we're going to construct a +4 confidence interval. All right, again, we need to check all of our conditions. So the first one is our independence assumption. So we have no reason to believe that one person being a home fan will affect another person. All right, randomization condition. The people in line were randomly selected. 10% condition. 81 people are likely to be less than 10% of the fans in the stadium. All right, success failure condition. As previously mentioned, this condition is not met since there are at least 10 non-home fans in the sample. Since the other conditions are met, we can construct a 1 proportion plus 4 z-interval to estimate the percentage of home fans at the game. Okay, so what I like to do first, and I'll show this here later. Okay. Hopefully I can get back to this. Okay, so I like to go ahead and find my new p tilde. So p tilde is going to equal 73 plus 2 over 81 plus 4. So that's going to give me 75 over 85. All right. And if I do that on the calculator real quick, okay, I'm just going to pull that out. 75 divided by 85, and I get 0.882. Okay, so if I was to construct this by hand, it would be p tilde plus or minus z star times the square root of p tilde q tilde over n tilde. So that would be 0.882 plus or minus, and we're going to construct a 95% confidence, 1.96, times the square root of 0.882 times, let me subtract 1, 0.118 over 85. All right, and we should get somewhere around 0.814 to 0.951. All right, and again, you could actually do this on a calculator by going to 1 proportion z interval. Again, by going to stat, test, option A. Okay, so now let's go ahead and write up our conclusion. Okay, so I would say the following. We are 95% confident that between 81.4% and 95.1% of all people are home fans. Right. Now, here's some shocking news for you. Nobody's perfect. Even with lots of evidence, we can still make a wrong decision. So when we perform a hypothesis test, we can make mistakes in 2 ways. Okay, way number 1. Okay, the null hypothesis is true, but we mistakenly reject it. We're going to call that a type 1 error. Okay, or the null hypothesis is actually false, but we fail to reject it. That's a type 2 error. Okay, so I like to think of these like this. So the null hypothesis is true, but we mistakenly reject it. So basically, we found an innocent person guilty. Whereas if the null hypothesis was false, what we failed to reject is that we found a guilty person not guilty. Okay. Now I actually like to think of this chart that I have on the next page. So which type of error is more serious depends on the situation at hand. In other words, the gravity of the error is context dependent. So here's the illustration of the 4 situations in the hypothesis test. So the null hypothesis along the top can be one of 2 things. It's either true or it's false. and we make two decisions. We either reject a null hypothesis or we retain a null hypothesis. So if I throw out a true hypothesis that's wrong, we call that the type 1 error. If I throw out a false null hypothesis, that was the correct decision. Check. If I retain a true null hypothesis, correct decision. And if I retain a false null hypothesis, that was a type 2 error. And then we're going to learn real quickly that the probability of making this type 1 error is going to be equal to alpha. And the probability of making a type 2 error, we're going to call beta. Okay? So how often a type 1 error will occur? Well, since the type 1 error is rejecting a true null hypothesis. And when do we do this? Well, we reject a null hypothesis when our p-value is below alpha. So this is directly related to alpha. Therefore, the probability of making that error is our alpha level. Okay. Whereas, or when a null hypothesis is false and we reject it, we have done the right thing. So this is a very important definition. A test's ability to detect a false hypothesis is called the power of the test. So if I look back at my chart, the test's ability to detect a false hypothesis. Here's a false hypothesis. The exact opposite of that. Okay, this is the only one that's, I can't detect a false hypothesis, is beta. So the exact opposite of that is the power. Okay, so we can also define the power as equal to 1 minus beta. So when the null hypothesis is false and we fail to reject it, we have made a type 2 error. We assign the letter A to the probability of this mistake. When the null hypothesis is false and we fail to reject it, this should be beta, so correct that. Okay, it's harder to assess the value of beta because we don't know what the value of the parameter really is. There's no single value for beta. We can think of it as a collection of betas, one for each incorrect value. Okay. One way to focus our attention on a particular beta is to think about the effect size. Okay. And we ask ourselves, how big of a difference would matter? We could reduce beta for all alternative parameter values by increasing alpha. Now, this would reduce beta, but it would automatically increase the type 1 error. This is the tension between a type 1 and type 2 errors is inevitable. So the concept here is this is an inverse relationship. Okay. When you decrease one, either alpha or beta, you will increase the other. All right, so here's example 10. So for each of the following situations, state whether type 1, type 2, or neither error has been made. All right, so a test of the null hypothesis P is 0.8 versus the alternate hypothesis P is less than 0.8 fails to reject the null hypothesis. Later, it was discovered that P is actually equal to 0.9. So we failed to reject the null hypothesis. Okay, our alternate was that it's actually less than. So we wouldn't conclude it was less than. Did we make the right decision? Yes, we did. So this was no error has been made. Okay, because we know it's not 0.8, but our alternate said it was less than. So we failed to reject. That means we have to stay with the steady state, basically rejecting our alternate hypothesis. Okay, B. A test of the null hypothesis is P is equal to 0.5 versus the alternate P is not equal to 0.5 rejects the null hypothesis. Later, it is found that P is actually 0.65. I rejected it, that it was 0.5. I found out it wasn't 0.5. That's a correct decision. No error. All right, a test of the null hypothesis P is 0.7 versus P is less than 0.7 fails to reject the null hypothesis. So I'm keeping it that it's 0.7. But later I found out it's less than 0.7. That was my alternate. I didn't do it. Well, that was an error. Okay, so I failed to reject a false null hypothesis. This is a type 2 error. So the power of a test is the probability that it correctly rejects a false null hypothesis. When the power is high, we can be confident that we've looked hard enough at the situation. The power of the test is 1 minus beta. Because beta is the probability that a test fails to reject a false null hypothesis, and the power is the probability that it does reject it. Okay, so it's the reverse of the situation. Whenever a study fails to reject its null hypothesis, the test power comes into question. So when we calculate power, we imagine that the null hypothesis is false. The value of the power depends on how far the truth lies from the null hypothesis value. So the distance between the null hypothesis value, P0, and the truth, P, is called the effect size. Power depends directly on the effect size. A picture is worth 1,000 words. Okay? The larger the effect size, the easier it should be to see it. Obtaining a larger sample size decreases the probability of a type 2 error, so it increases the power. It also makes sense that we will be more willing to accept a type 1 error. So the less likely we'll be to make a type 2 error. This diagram shows the relationship between these. So this is the null hypothesis is true. Okay. Here's alpha. This is also the probability you make a type 1 error, probability you make a type 2 error. So if I move this line this way, notice I increase alpha, but I will decrease beta. Okay, so there's that inverse relationship there, and the vice versa can happen. So the previous figure seems to show that if we reduce the type 1 error, we must automatically increase the type 2 error. But we could actually reduce both types by making the curves narrower. How do we do that? We increase sample size. Really, so the only way we can kind of reduce both alpha and beta is to increase the sample size. So this figure means that we are just far as apart as the previous figure, but the sample sizes are larger and the standard deviations are smaller and the error rates are reduced. So you see how you get smaller alpha and smaller beta by keeping P where it's at, okay? But you get everything else stays the same. So here's the original comparison, okay? So here's alpha, here's beta, here's alpha, here's beta. Okay, so we could move one or the other, but that's automatically going to increase or decrease the other. Or if we wanted to decrease both, we just increase our sample size. So AP tips. Be prepared to describe a type 1 or type 2 error would be in the context of beginning and set hypotheses and the consequences that could occur. You can choose any alpha level you would like to do, but most choose 5%. I recommend that. Once in a while in AP tests, we ask for specific alpha level to be used. If it does, follow the directions. So here's example 10. Spam filters try to sort your emails, deciding which are real messages and which are unwanted. One method used is a point system. The filter reads an incoming email and assigns points to the sender, the subject keywords in the message, and so on. The higher the point total, the more likely it is the message is unwanted. The filter has a cutoff value for the point total. Any message rated lower than the cutoff passes through your inbox, and the rest is suspected to be spam or diverted to the junk mailbox. We can think of the filter's decision as a hypothesis test. The null hypothesis is that the email is a real message and should go to your inbox. A higher point total provides evidence that the message may be spam. When there's sufficient evidence, the filter rejects the null, classifying the message as junk. This usually works pretty well, but of course, sometimes the filter makes a mistake. So example 10. When the filter allows spam to slip through your box, which kind of error is this? Okay, so I'm going to type this in here. All right, so this would be, all right, so let me bring this size down to 12. Okay. So this is a type 2 error. The filter decided that the message was safe when, in fact, it was spam. Okay. Well, let me go ahead and make this even smaller so it fits on one line. There you go. All right, let's go to the next one. Okay, so for part B, what kind of error is it when a real message gets classified as a junk? Well, that's a type 1 error. The filter decided that the message was spam when in fact it was not. Some filters allow the user to adjust the cutoff. Suppose your filter has the default cutoff of 50 points, but you reset it to 60. Is that analogous to choosing a higher or lower value for a hypothesis test? And explain. All right, so let's do this. Oops. All right, so let's do this one. So C. So this is analogous to lowering alpha. It takes more evidence to classify a message as spam. All right. What impact does this change in cutoff value have to the chance of each type of error? Oops, where am I at here? Okay. Okay. All right, so the risk of type 1 error is decreased, and the risk of type 2 error has increased. All right, example 11. So consider again the points-based spam filter described in the previous example. When the points assigned to various components of an email exceed the cutoff value that you set, the filter rejects its null hypothesis that the message is real and diverts the message to your mailbox. In context, what is meant by the power? Okay, so let's try this one. So I would say the following for power. So the power of the test is the ability of the filter to detect spam. What could you do to increase the filter's power? All right, so I would say this. To increase the filter's power, you lower the cutoff score. What's the disadvantage of doing this? All right. Okay. So if the cutoff score is lowered, a larger number of real messages would end up in the junk mailbox. All right, and then example 12. So testing for Alzheimer's disease can be a long and expensive process consisting of lengthy tests and medical diagnoses. Recently, a group of researchers devised a 7-minute test to serve as a quick screen for disease for use in the general population of senior citizens. A patient who tested positive would then go through the more expensive battery of tests and medical diagnoses. The authors reported a false positive rate of 4% and a false negative rate. All right, so A, put in context of the hypothesis test. What are the null and alternate hypotheses? What's a type 1 error? What's a type 2 error? Which is worse? And then E, what is the power of the test? Okay, so let's go ahead and answer these questions. So this is example 12. Okay, A. So the null hypothesis is that a person is healthy. The alternative is that they have Alzheimer's disease. There is no parameter of interest here. All right, B. A type 1 error is a false positive. It has been decided that the person has Alzheimer's disease, and they don't. All right, C, type 2 error is a false negative. It has been decided that the person is healthy when they actually have Alzheimer's disease. All right, D, a type 1 error would require more testing, resulting in time and money lost. A type 2 error would mean that the person did not receive the treatment they needed. So a type 2 error is much worse. And then lastly, part E, the power of this test is the ability of the test to detect patients with Alzheimer's disease. In this case, the power can be computed as 1 minus the probability of a type 2 error which equals 1 minus 0.08, which equals 0.92. All right, example 13. So a company is willing to renew its advertisement contract with a local radio station only if the station can prove that more than 20% of the residents of the city have heard the ad and recognize the company's product. The radio station conducts a random phone survey of 400 people. So A, what are the hypotheses? B, the station plans to conduct a test using a 10% level of significance, but the company wants the significance level lowered to 5%. Why? What is meant by the power? For which level of significance will the power of this test be higher and why? And then finally, they agreed to use alpha equals 0.05, but the company proposes that the station calls 600 people instead of 400. What will make the risk of type 2 error higher or lower, and explain. All right, on our last example. So example 13. A. So my null hypothesis, H naught, is going to be P is equal to 0.20. And then my alternative hypothesis, I'll call HA, is going to be P is greater than 0.20. All right. B. So the company wants more evidence that the ad is effective before deciding it really is. So by lowering the level of significance from 10% to 5%, the probability of type 1 error is decreased. The company is less likely to think the ad is effective when it actually is not effective. Let's see. The power of the test is the probability of correctly deciding more than 20% have heard the ad and recognize the product when it's true. D, the power of the test will be higher for a level of significance of 10%. There is a greater chance of rejecting the null hypothesis. E, increasing the sample size to 600 will lower the risk of a type 2 error. A larger sample size decreases variability, which helps us notice what is really going on. The company will be more likely to notice when the ad really works. All right, and that is the end of the notes.